Hello, everybody. Okay. Welcome to the IMS Medallion section, Medallion lecture section 1. My name is Jiashun Jin, and I'm professor at Carnegie Mellon University. It's my great pleasure today to introduce today's Medallion lecturer, Professor Ery Arias-Castro. Ery is currently a professor at UC San Diego in the Department of Mathematics and at the Halesoglou Data Science Institute. He did his undergraduate studies in mathematics at École Loma Supérieure Paris-Saclay and the University of Paris. He received a master's degree in artificial intelligence and applied mathematics from École Loma Supérieure Paris-Saclay and a PhD degree in statistics from Stanford University. After that, he took a short postdoc position at IPAM in Los Angeles and another one at MSRI at Berkeley. He joined UC San Diego as a faculty in 2005. He's an elected IMS fellow. Ery is actually one of my academic brothers. We went to Stanford University for our PhD study at the same time in 1999. And we both have David Donahoe as our thesis advisor. As far as I know, he's a well-achieved and a very modest researcher. His research interest spans many areas in statistics, machine learning, signal processing, and applied probability. He has authored a book entitled Principles of Statistical Analysis, and he has co-authored close to 100 papers, and several of his papers are my favorite. These include his papers on detection of geometric objects using multi-scale methods. I recall a time Tony Kai and I have studied this paper very carefully together. This also included his paper on network community detection and his long list of work on detection of sparse and weak signals. In my eye, Ery is one of the very few statisticians who knows the best about detection of sparse and weak signals and have certainly learned a few tricks from his work. Each year, IMS nominates 8 Medallion lecturers in fields across the IMS subject range. The award of a Medallion lecturer signals the honor inherent in being selected to give one of these lectures. Today, IMS awards Medallion lecture to Professor Ery Arias-Castro and invites him to present a Medallion lecture entitled Modal Clustering, Past and Present. Okay. So here's a medallion.
Thank you very much, Jiashun. It's a true honor. So I'm going to talk about not detection of sparse signals, but about a different topic I've been interested in for quite a while, in fact. And within that, so that's clustering, and within that, I will specialize into what is typically called modal clustering. And this talk involves a lot of foundation, some technical work as well, but a lot of it is also just at the level of foundational, what is clustering? It's joint work, so this started, in this particular line of work, I started working on with David Mason and Bruno Pelletier about 10 years ago, and more recently with Wally Jiao and Lisi Koda, one of my students. Right, so the talk is divided into multiple parts, all having to do with modal clustering. And in this first part, what I'll do is talk about how we try to bridge build a couple of bridges between two definitions of modal clustering and effectively try to equate them. So before the 1970s, as far as I was able to look into the history of this, there were two main approaches to defining what clusters in space I'm talking about are. Okay? One is fitting a mixture model. This goes back to, well, a long, long time, to Pearson in the late 1800s, it turns out. So it's not 1994, it's 1894. And the second way of understanding clustering at the time was direct partitioning. Think of k-means. And in the 70s, we'll see two approaches were proposed for defining clustering that were quite different from that, much more centered on the density. So the first one is, or can be found in the book, well, famous book by John Hartigan on clustering, in which most of the book is really about gathering what was known about clustering from various applied fields. And the book overall was is very much focused on algorithmics, and it even includes code. That's how code was shared before GitHub, I guess. And but at some point, I believe it's in chapter 11, he talks about defining clusters as the upper level sets of a density. So suppose that we have a density F, which in statistics we effectively equate with the population, as long, of course, as the population as density. That's on RDS. And again, we're talking about here clustering points in space. And the population cluster, so now we have to talk about at some level, so at some level T, are the connected components of the upper level set of F at level T. Okay. How does the sound look? How does it sound when I move my head? Sounds okay? Okay, because at some point there's echo and there's no echo, so it's a bit bizarre for me. Okay, so it sounds fine when I speak here? Yeah? Okay. It sounds very different on my side.
Yeah, those goosenecks pick up pretty good.
One time?
Those goosenecks pick up pretty good, so that speaker, you should be good.
Okay, so I can talk in this direction I'm hearing?
Yeah, it doesn't matter where you turn your head, you should be fine.
Okay.
I'll adjust accordingly.
Good. I just want to make sure.
Perfect, yeah, you're good.
Okay, all right.
Yeah.
Okay, so we'll see that. So then the question arises, what happens outside of the upper level set, right? Okay, so we'll talk about it a bit later. So here's a pictorial representation of this. I believe this is a mixture of 4 Gaussians in dimension 2, and the colors are simply the height, and the contour plot, and the lines represent level sets, not upper level sets, just the level sets at various levels. All right, so 2 important issues with this definition. One of them is that the choice of level T is not at all obvious, although this could be just in a sense treated as any other parameter, and you could imagine selecting it here. If there's density, perhaps you can do cross-validation. That could be possible, I guess, if you have some sort of something to optimize. Not clear what, but you could try to come up with something. And but that's not the way Hartigan thought about this. He thought about this as being really an exploratory approach to data analysis, in which case it's just more natural to not define T, a single T, but explore multiple values of T. Okay. The second issue is that it's not clear what we should do with what's outside the upper level set at level T, assuming some level T is chosen. Again, it's not clear from point 1 that we should do that anyway. And but if we do it, then it's not clear at all what is done outside that upper level set. And it's often treated as noise, effectively. All right, so that's one of the definitions I was referring to. The other one also appeared, so the book actually was published in 1975, the same year. So the first name, I'm going to butcher it, but Kenosuke Fukunaga and Larry Hostetler published a paper in Transactions on Information Theory, also on clustering, advocating for a method, if you can read there, of clustering a set of observations into different classes, assigning each observation to the nearest node along the direction of the gradient. So, it sounds quite different. Those are the 2 methods that will, in fact, show that they are very closely related. All right, let me go into more detail here. So again, we have a density F on some Euclidean space RD. Think of D as not being large because we're talking about the density that needs to be estimated at some point. And yeah, so the idea is to define a population clustering, so partition of the support of the density by taking each point in the support and moving it upward according to the gradient ascent flow of the density. Okay? And so people in dynamical systems, let's say, would define basins of attraction. So if you have here it will have to be a critical point X star, and the basin of attraction associated with X star is the set of points in the support of F where if you start there, the gradient ascent line ends at X star. Okay? All right, so under some regularity conditions, here I leave them as if they were a bit mysterious, related to Morse theory. Actually, the conditions are not difficult. It's just that effectively you want F to be effectively something like twice differentiable, and the local maxima to be non-degenerate in the sense that the Hessian is negative definite there. That's more or less it. But the Morse theory says quite a bit. It says that almost all points, this is, for example, with respect to Lebesgue measure, almost all points in the support of F belong to the basin of attraction, not of just any critical point, but of a mode, meaning a local maximum. A mode is same as, just a different word for, different terminology for local maximum. And so the population clusters in this, I guess, from this perspective, are defined as the basins of attraction of the density modes. Okay, so here, same Gaussian mixture that we saw earlier, and now this one has 4 modes, and here are a number of gradient ascent lines starting at the square points, which are just points in the support of this density. Okay, and here the overlay is not perfect, but anyway, here the those are the basins of attraction associated with those 4 modes. Okay, they each one have a color. So it provides a partition of the entire space, again, up to a set of measure 0. That's what Morse theory tells us. Okay. It turns out this approach to clustering has been rediscovered multiple times, including not too long ago, I mean almost 20 years ago now, but anyway, not too long ago. So anyway, so our first contribution is to build, in fact, 2 bridges, 2 different perspectives on how to, in a sense, equate those 2 definitions of clustering. And in fact, those definitions of clusterings and related ones are, in fact, already talked about, or were already talked about under the same umbrella name of modal clustering, which is also the title of this talk. So here, like I said, we argue in 2 different ways that the gradient ascent flow is, in fact, in a sense, if you want to extend Hartigan's definition, which goes better with, again, what we would call a cluster tree, like a hierarchical cluster. Maybe if you want like what's called a flat clustering, just a partition of the space into clusters. Here I'm talking about population clusters. Then the way to do it is with Fukunaga and Hostetler's definition. That's the idea. So the first bridge is based on effectively looking at an analysis of it, and showing that the gradient ascent flow allows you to effectively travel the cluster tree. So F is the density on RD again. This is the upper level set I was referring to earlier. This is the level set I was also referring to earlier. Those are the, when you vary T, this is what gives the lines in the contour plot. And so we assume that F is twice differentiable. In fact, we assume a bit more than that, but let's say, so twice continuously differentiable and compactly supported, for example, will do. And in that case, the gradient ascent line, so the gradient flow can be shown. This is classical. So if the function, let's say, is twice continuously differentiable with compact support, then the gradient is Lipschitz, and that's enough, it turns out, for the gradient ascent flow to be well defined for all time. And it's defined right here. So if you start at a little x, then yeah, you just follow the gradient upward. Right. Right. So let's assume that F is Morse, meaning that the local maxima are non-degenerate. Effectively, if we again say that F is twice continuously differentiable with compact support, what's left to be Morse effectively is that its maxima, local maxima are not degenerate. And in that case, we saw that a central result in Morse theory is that for almost all points in the support of F, the gradient ascent line ends at the mode, okay? As opposed to something like a saddle point. Okay? And the first result we have is that if we take such a point, one whose line does not end at the saddle point but ends at the local mode, then its gradient ascent line is compatible with the cluster tree in the sense that it does not cross from one connected component to another at the same level. Okay. In the other direction, we also show that there's another compatibility that goes in a sense in the other direction. So here we have to imagine what it means to, if you ignore gradient ascent flow for now, and if you're only looking at the cluster tree, which is again this tree structure, sorry, I didn't define it properly, but this tree structure that's given by the upper level sets when you change the level T. A natural way of moving in that cluster tree would be to, say, discretize the levels and then move from one to another by, for example, metric projection, meaning you go from one to the other by, if you start at one point, you go to the closest point in the other set, okay? And it turns out that that's well defined as long as the level T is non-critical, meaning on the level set LT at T, there's no critical value. And if, in that case, if eta is small enough, then LT and LT plus eta, so the level set at T and the level set at T plus eta are in one-to-one correspondence, diffeomorphically, in fact, with the help of the metric projection. Okay? So let's, in that case, define PT eta as a projection from that level set at level T to the level set at T plus eta. Assume that T is non-critical and it is going to be small. So what is the connection with the gradient ascent flow in that case? It comes from letting eta go to 0 and looking at when you go from one point at level T and move it by metric projection to a level T plus eta. When eta is small, then in fact the vector, the move you're making is almost along the gradient of the density at that location. That's what this result says. So the move, if you see that's right here, it's on the right-hand side, and then when you let eta go to 0, it converges to effectively something proportional to the gradient at that location. So this will lead us, if we just in that case consider eta as being infinitesimal, and we are moving up the cluster tree by, if you want, successive metric projections, then it will lead us to considering this flow here. But this flow is the same, it actually traces the same gradient ascent flow except at a different speed. So in other words, that's another way of establishing, if you want, that if you move up the cluster tree in a fairly natural manner, you end up with a gradient ascent flow. So we sort of went in both directions. In fact, if we stay with this one, we took a bit more of an algorithmic stance on this that seemed a bit clearer to us, to again draw a connection, a second bridge, if you want, between those two definitions of clustering. And well, let me just show you how it goes. So here again, I'm just defining clusters at the population level. Of course, you could always do a plug-in if you have an estimate for f hat. You could apply something like this to f hat. That's going to be the next part. But for now, we just have f. We just want to define what the clusters are at the population level, so meaning based on f itself. Okay? So to even know what we want, what we are after, assuming we want to perform statistical inference and we have a sample of points in front of us. What are we after even? Okay? All right. So the idea is this: is that we discretize the levels and we do metric projections successively. And we go in, well, it's very similar to what I just mentioned, this second bridge, sorry, when we were going in the other direction. But here we see this as, in a sense, an algorithm defining the clustering based on F. At the end here, we have to make sure that we don't jump from, that we remain within the cluster tree. That's all the last part says. And yeah, So this discretization is vertical, and it's by eta every time. We also, in the same paper, we looked at the horizontal discretization as well. But anyway, I'm going to focus on this one. And the result is this: like, if we start from the point x in the basin of attraction for, again, the gradient ascent flow of f of some mode x star, then for eta small enough, so it doesn't have to go to 0. But it has to be small enough in a way that depends on the starting point x. The algorithm I just mentioned, which is, again, jumping my metric projection from one level set to the next, when initialized at x ends up at x star, the last jump is actually, is a bit special. You have to look at the algorithm. I won't spend too much time, but the last jump is effectively just jump to the maximum if you cannot, if the discretization ends there, effectively. Okay. And also, as eta goes to 0, the whole polygonal line that you're tracing by doing those metric projections successively approaches the gradient ascent line in something like Hausdorff distance. So that's another way we link the two, is that, again, so it's continuing in a sense with the previous project or paper, and this one pushing it a bit further in that if we move in a fairly natural manner, which is by successive metric projection, up the cluster tree, we end up with the gradient ascent flow as long as density is smooth enough. Right, so now moving to actual methods. So, so there's a whole, so we didn't do this. This is just to point out that I guess going with Hartigan's definition of clustering based on level sets, there is a whole literature on the estimation of level sets. And also on the estimation of the cluster tree, in which it turns out single linkage plays an important role. That variant of hierarchical clustering is particularly demonized, but it turns out that is the most natural in the context of modal clustering. Now, it has to be regularized, and it also, it's sort of a misunderstood algorithm, although John Hartigan, almost 45 years ago, knew how to use it. It's just like it's been lost somehow. People complain about chaining, that sort of thing, but it's just based on misunderstanding on how to use single linkage. Anyway, I won't say much more than that, but other than regularized versions of single linkage such as dbScan are shown they are known to estimate the cluster tree under some standard regularity assumption on the density. All right, so that's on one side. On the other side, there's also a whole literature, algorithmic methodology literature on Fukunaga's perspective on clustering. The one, again, based on the gradient ascent flow of the density. And the last one, in fact, here, this paper is the paper I have together with David Mason and Bruno Pelletier about 10 years ago. So we worked on this, but there was already quite a bit of work on the topic. And here I'm only listing some more theory-oriented papers. There are many more applied papers around what's called mean shift, which is, we'll see it. That's sort of the name that goes with Fukunaga's approach to clustering. Okay. There's also a surrounding literature on estimating the gradient lines, which as you can imagine, is very closely related, and also other features of density, such as density ridges. So what we do here is we have a paper where we analyze a bunch of those methods combined, and in fact, for the first time, we show that, as far as we know, we show that mean shift is consistent. So what we do is we have a if you look at the paper, we have a prototypical method that we call hill climbing, in the sense that if you see the topography given by the density, it goes up. And we look at both algorithmically, in the sense that if we know f, are we consistent? And if we don't know f, but do a plugin, are we consistent as a method? Okay? And we do both. So the first one and simplest one is not the mean shift. So there's a bunch of them, and I'll list a few of them. This is called the max shift. It's possibly the simplest method one can think of, which is that and I should say algorithm as opposed to method, at some point, starting point x0, let's say, so the method algorithm has the parameter epsilon, you move to the point with highest density within distance epsilon, and you do that recursively. Okay? So it's such a natural method. We only found it after the fact in some paper on topological data analysis, but it's not as it's not quite as common as we would think it would be. Nonetheless, we are stating the result itself, which is what I said. Like it's consistent in the sense that you recover the basins of attraction effectively when epsilon effectively goes to 0 here, and when you have a method, we estimate f by f hat. We apply this, and we show that when epsilon goes to 0 and n goes to infinity, n being the sample size, with the bandwidth properly selected in a standard manner, as a method, it's also consistent. Like we also recover the basins of attraction asymptotically. That's what I mean here. It's just one sentence, but I mean a lot here by this sentence. So that's one method that we study. We study another one. We call it Euler shift. This is simply implementing a Euler scheme on approximating or computing, if you want, the Grant ascent lines. In fact, that's a method that we analyzed together with David and Bruno about 10 years ago. And we already showed there it was consistent, but in that same framework, we are able to also show it's consistent, both as an algorithm and also as a method. This one has one parameter as an algorithm, rho. And of course, when you see it as a method, meaning when you have to estimate f, you have to deal with the bandwidth. But again, there's no secret there. The bandwidth is estimated in the usual way. All right, and last but certainly not least is mean shift. So what is mean shift? Is the most well-known whatever shift method in this whole line of work. And so let me actually move forward here. Okay. So it turns out that there are two main variants of mean shift. The first one actually suggested in that same paper by Fukunaga and Hostetler in 1975. In that one, they move all points, and then they move all points, and they move all points, and the mean shifts are done with respect to the new points every time. Okay? The method that Chang proposed about 20 years later in 1995 fixes the original points and then as if moves copies of the other points with reference to the original points every time. Okay? And it turns out that the behavior is quite different. The second one is the one we are referring to when we say mean shift. Okay? So what is this MS sub H? So if you're at point X, the vector you're deformed by moving, if you want, to the center of mass of this KH. K is going to be a kernel. KH convolved with F, centered at X. Okay, so you move to the barycenter of that smoothed version of F. Okay? That's why it's called the mean shift. Is you move to the barycenter, to the mean. Right, and then you just define a sequence based on that. So at point X, I guess I called it X0 perhaps earlier, but anyway, same thing. You start somewhere at X, and then recursively you move by mean shift effectively. Okay, and the parameter here is H. I'll show why it's related to the Grant ascent flow in a second. So this is, as I said, the most well-known method, and there's been some work on showing that it's sort of converges somewhere, but I think we are the first ones to show that it actually converges as it should. So it is consistent, again, at recovering the basins of attraction, both as an algorithm, and if you know F, you just do this and you let H go to 0, and also as a method where in that case you have to deal with the estimation of F. So in both cases, we can show that it's consistent. So what is the connection with the Grant ascent flow? This was already known to Chang. Here's a slight variant of his result. So if K is your usual isotropic kernel, then you can define this other function L, which also turns out to give rise to a isotropic kernel of its own. And then when you scale them with an H, that's what defines M sub H. It's right here. Okay. So think of H as being small, in which case LH convolution with F will be close to F, right? And KH convolution with F will be also close to F. Yeah? And all of a sudden you have what? You have something like that depends on H squared in front, which will give you the step size. And then you have a gradient of F over F. Okay, so that's also following the gradient ascent line when H becomes small. Actually, I have it here. I forgot it. Okay. That's the connection. And yeah, so anyway, we're able to, with some stability result, we're able to show that it's also consistent. This requires a bit more work. But overall, this is our method of proof for all of those methods. So it's very standard. So for the algorithm, meaning when we know F, this is very standard. It's actually taught at the undergrad level here in the US when showing that the Euler method is consistent for the for wherever it's made, I guess. And so what's done is like near a mode, just to show that you have to increase, and because you stay within the couplet if you want, you have to end at the mode. And away from the mode, you have to just show that you don't stray too far away from the gradient ascent line, and that's typically done with some sort of ground wall inequality. So that's very standard. But anyway, we spell that out, and each time we have to adapt a little bit the arguments for each one of the methods. But for the method now, this requires a bit more work, and it's based on the perturbation analysis. Showing that when you go from F to F hat, things like the gradient ascent line doesn't change too much. Okay. It's also fairly standard. All right, so continuing with the same topic, we had a smaller project on looking at whether we could build a hill climbing method for graph partitioning. So now I'm talking about partitioning a graph, no longer clustering points in space, but as soon draw a relationship. I mean, it's a standard one. Okay, so imagine you have an undirected graph. Let's just say it's labeled by 1 through n without loss of generality, and the adjacency matrix is A, and that's all we have. So we are provided with the the graph is given to us through the adjacency matrix A. Okay. So things that people do when performing graph or considering graph partitioning is things like optimize a notion of cut. Okay. And so, for example, you could do bisection into two subsets of same size, assuming that n is even, and that's how you define the cut in that case. Simple notion. Okay, so you will try to minimize that. And in this context, so I guess it wouldn't be hill climbing; it would be hill descending, I guess. But in that case, you could, of course, consider the negative of the cut. Typically, in this setting, applies to the topography not given by some sort of density, there's no density here, but given by the function to be optimized, right? That's what it means to be hill climbing or hill descending. Okay. So, like a prototypical method here would be to start somewhere, and then either at random or some sort of special graph partitioning, and then go downhill from there, as if you were to do gradient descent to optimize to minimize the function. Okay. And it's actually not that naive. There are papers that show that doing that is a good thing. In fact, it's been done a lot. It's been done a lot. In fact, often as a refining step. Like I said, for example, I believe it's this paper by Modal, Niemann, and Sly that they have effectively as a spectral method, but then they do a refinement based on what I'm just mentioning. Node swapping effectively. This goes back at least to the 70s. Like I say here, there's a famous algorithm by Kernighan and Lin, who is actually quite sophisticated. But things like the PAM algorithm for chemedoids is also of this type. And although that's not for graph partitioning, but for clustering points in space, there's a variant of an algorithm by Hartigan and Wong for k-means that's also of this type. Okay. So what we do here is we define a method that's hill climbing in the other sense. But for this, I have to make a connection because there's no density right now, right? The connection is through a random geometry graph. So the idea is that when the graph is a realization of a random geometry graph, then approximately the algorithm I'm going to define soon does hill climbing in the Fukunaga sense, if you want, okay? On the underlying density that is at the basis of that random geometry graph. All right. So, let's define the degree function, which I guess we called Q for some reason. So Qi is the degree of node I in the graph. And we call this graph max shift. You see why? It's very closely connected to with max shift. So when you start at some node I, what you do is you successively move to the neighbor with highest degree, and if there are some ties, you just break them any way you want. Let's say at random. Okay. All right, and then how do you form clusters? Of course, you cluster nodes where if you follow this process, you end up at the same node. And we have to do some tweaking at the end in which, this is very common, by the way, in this type of method, that we do some cleaning at the end in which if you have two representative nodes, meaning nodes with maximum local degree, let's call them, if they are within a few hops of each other, then we merge two clusters that they represent. We found actually this method somewhere. It turns out in a recent paper. And now it's proposed for entirely different reasons. Because of that, the authors don't do the sort of analysis that we have in mind here. In fact, they come from their motivation is changing. Actually, I'll talk about it a bit later, but there are some papers that say if you assume those axioms, then some clustering algorithms that satisfy those axioms, well, none of them exist. Okay? I'll talk about actually right after this. And that's where they come from. They come from challenging such axiomatic approaches to clustering. So anyway, it's a different, completely different perspective. Nonetheless, the graph max shift is a special case of the class of clustering algorithms they consider in that paper. All right, so let's make a connection with points in space and their clustering. So let y1 through yn be points in some RD. And then let's consider a connectivity radius epsilon and form the corresponding neighborhood graph, meaning that we connect 2 points that are within distance epsilon. Okay? So, and you have to imagine that the graph is still indexed by 1 through n, but 1 is connected to y1, y is, represents y2, and so on. And the connection is simply what I have here, that aij is 1 if yi minus yj, so yi and yj are within distance epsilon, and 0 otherwise. Okay. All we're given again is the adjacency matrix in principle. Okay, so we have no idea whether this is how the adjacency matrix is built. Nonetheless, let's consider applying a graph max shift to a graph like that. And it turns out that it computes the same hill climbing paths as max shift, therefore the name, when estimating the, I guess, density. So here would be, I haven't even talked about the density, because as if you were looking at those, that point cloud, y1 through yn, and then estimating their density, assuming one exists, okay? Using the so-called flat kernel. Some people call it naive kernel or uniform kernel. So effectively, it's just a constant kernel, so flat, and then it comes to 0. Okay, sorry, I should say one more, in that when choosing the bandwidth to be epsilon and the search radius to also be epsilon. So remember that MaxShift has search radius as well. Okay. So why is that? So if we consider doing this kernel density estimation with bandwidth epsilon using that kernel, then you'll see that when you compute it, you have exactly the sorry, it's here. So you have the degree. So sorry, when you evaluate the estimate at yi, you have the degree qi, divided by something that does not depend on I. Okay. So in other words, the value of the kernel density estimator at yi is proportional to the degree of node I. Okay. So for that reason, if the search radius for MaxShift is also epsilon, so not just the bandwidth used for the KDE, but also the search radius, they're both the same and equal to epsilon, then when we apply graph MaxShift to such a graph, what we're effectively doing is MaxShift with that kernel, that bandwidth, and that search radius. Okay. So you see the connection. And we're able to prove this. So this is not exactly so the proof technique is not that different as you could imagine, but it's not a corollary of our previous work. It's just because here the kernel is not smooth enough to estimate the density at enough of a precision to the perturbation analysis that we do in the previous paper. But nonetheless, we just take a direct approach using more or less the same technique. And we're able to prove that now if the yi's are not just fixed, but are themselves randomly generated from some density, so ID from some density f. This is where density f comes in. And then what we do is we choose the tuning parameter. So tau is the number of hops when we merge clusters. So it just has to be large enough. And then epsilon n, we don't have a control over. But if epsilon n goes to 0 slowly enough, then the procedure is consistent in the same sense that it was before. We recovered the basins of attraction. So again, here the difference is that we don't have a control over epsilon. We're just given the adjacency matrix, and the only tuning parameter, I guess, is tau here. Okay. And it just has to be large enough. And it sort of works in practice. This is not meant to be a method that competes with anything, to be honest. It's again more at the foundational level. But it sort of works. So this is just proof of concept. Right. And for the last part, it's also foundational, and it's considering, in fact, what I mentioned just a few minutes ago on an axiomatic approach to clustering, but here an axiomatic approach to hierarchical clustering. Actually, there has been a lot of work on trying to set some axioms for clustering. So literally just what does it mean to do clustering? And one way to come up with a definition is to start with some axioms. What's desirable about clustering, right? What should clusters be, right, or satisfy? So that's actually true both on the side of flat clustering and also on the side of hierarchical clustering. And here we'll focus on hierarchical clustering. So there's a bunch of papers, a lot of them in computer science. One of the famous ones is one by Kleinberg in 2002, in which this one is famous because it's a non-existence result. It comes up, it has 3 axioms and shows then that no algorithm satisfies them, although at the end of the paper, he softens one of the conditions, one of the axioms, and shows that some method satisfies them. In fact, surprise, surprise, single linkage does. And so you see there starts to be a connection there. And that softening of the axiom is perhaps even more natural than the original one, but the shock value was worth it, I think. And it definitely generated a lot of interest on that question. That's for flat clustering. But there also has been some work on hierarchical clustering, in fact, from the 1960s and on. And it turns out again that, despite being maligned, once you got the level of axiomatic clustering, the single linkage appears again and again. It's very interesting. So how much time do I have? Because I don't know if I have time to go through this. 5 minutes? Oh, I have a lot of time? Okay. So I'll probably take another 10 pops, something like that. Okay, so it's going to be on another pops 10 minutes at most. So, right, so what we do is, so in almost, I would say, possibly all of them is on the discrete side. So, the clustering of points as algorithms that return, partitions. If the points are indexed by 1 through n, let's say, right, the return is a partition of 1 through n, okay, into cluster labels. And here we continue with a density and the definition of what it means to do hierarchical clustering of the density. Okay. It turns out we recover Hartigan's definition here. So again, like at some point you'll have to see if you're convinced by our axioms or not. One of them is very close to his definition of clustering. So, but anyway, I'll challenge you to think of whether that makes sense or not, or at least if it's convincing. But we in fact recover hierarchical, the cluster tree as defined by John Hartigan. And here there's not like a tension with the gradient ascent thing, because we're not looking at what's called flat clustering, meaning like a partitioning of the support. We just literally only care about hierarchical clustering, so that the cluster tree structure that Hartigan at least implicitly defined in his book. I think actually the definition was explicit, but effectively put the attention on, I think, at least implicitly. Right, so most of what we do applies to a metric space. You see why there's not like, we don't need to differentiate anything. So let's just, the space is going to be just your usual metric space with the usual assumptions. And okay, so a few definitions. What is the hierarchical clustering? Or a cluster tree of some subset X. So X is, here will play the role, of course, of the support of the density. You have to have a dominating measure as well. But just think about, if nothing else, omega being just a Euclidean space with a Euclidean metric. That's fine. And yeah, so what is that cluster tree, or also hierarchical clustering, is a collection of connected subsets of that set, which we refer to as being clusters. And a collection has a nested structure, meaning that two clusters are either disjoint or one is inside the other. Okay. And the Hartigan cluster tree is the one I defined earlier. But anyway, if you have a function f, it doesn't have to be density. But anyway, if you have a function f, then it's simply the collection consisting of the upper, the maximally connected. That's right. Sorry, connected components of its upper level sets. And it's indeed a cluster tree of the support of F. All right. So here are the axioms. One of them that we propose in the paper. So one of them is that the clusters are connected regions. In fact, we require a bit more. We require that they have a connected interior to avoid things like, you have like a domain here, and you have some sort of like a curve or something like, of dimension 1 connected them. So we want to avoid that. The second one is that, and sorry, there's one important thing, and I forgot to highlight it here, is like we start with piecewise constant densities, and then we extend them to continuous densities. So think about the construction of the integral, right? When you start with the piecewise constant, and then you extend to measurable functions, right? Both if it's Riemann or Lebesgue. So in their own way, so we do the same. We start with the piecewise constant densities and then move to continuous densities. So for piecewise constant densities, that's why this one I think makes sense, I hope. Axiom 2 doesn't really make sense unless you assume a piecewise constant density. So that's axiom 2. Regions of constant density are not partitioned. This one might be, in fact, the most controversial axiom, but anyway. And the third one is that clusters are high-density regions, implicitly surrounded by lower-density regions. Okay? So this is, in fact, what Hartigan says in his book. But again, even the English meaning of clustering means that you have a higher concentration of points, right? If it's points that we're talking about, right? So I think it makes sense to have that as one of the axioms. But again, you may or may not be convinced by that. But let me continue nonetheless. So, all right. So here is a typical member of this class of densities that we are discussing. Okay, so it has, in fact, finitely many constants of, regions of where it's constant, and yeah, it can be represented that way. And I think we require a bit more. We require that those AI have connected interior, and we also assume that the support of F has connected interior. If not, then effectively you treat the connected components more or less separately anyway. So it's not a big deal. But right, so script F is going to be the class of such densities or functions, if you want. They don't even have to be densities at this point, but of course when we do clustering, we are interested in them being densities, but it doesn't really limit us. Okay, so here's a crucial result is that if you take one of those functions, then there's a unique finest hierarchical clustering among those satisfying the axioms. And finest means that literally, if you look at all the cluster trees that satisfy the axiom, then there's one that contains all the clusters of any other one. Okay. So we're going to call that C star sub F. And we before moving forward, we regularize this script F function class a little bit, not by much, you'll see, but a little bit. And we make it F interior here, in which when we have two areas of where the function is constant, if we take the union of their closure, if it's connected, then the interior of that thing is also connected. So it's a bit of a technicality, but anyway, it's important. It seems to be important, at least in our arguments. And so when you have a function in that class, we are still talking about piecewise constant functions. Okay? When you have a function in that class, then it turns out that if you want canonical finest cluster tree, axiomatic cluster tree, coincides with the Hartigan cluster tree. So it's already, we're almost there. Of course, we're not necessarily interested in piecewise constant densities. So we want to extend that to, say, continuous densities. Okay, I'm pretty sure we could have extended that to piecewise continuous densities as well, but we only went to constant densities just to make a point, I guess. All right, so to do that, I'm going to define the merge metric, because I'm going to take now limits of piecewise constant functions. Think about building Lebesgue's integral again, right? And so I'm going to take limits of piecewise constant functions towards a continuous function, right? And then show that the hierarchical clusterings converge to Hartigan's tree for that continuous function. Okay, that's the program. So I had to define the notion of what it means to converge for the cluster trees, right? Okay. So for this, we use a merge metric, which was suggested, in fact, by some colleagues about 10 years ago. They're colleagues now. They were not at the time. So a dendrogram is a cluster tree equipped with a real valued non-decreasing function defined on the cluster tree called the height function. And so it's of the form C, where C is a cluster tree, and then H is this height function. And literally, H takes a cluster in that cluster tree and returns a real value, okay? And it's monotonic in the sense that, well, you see it here. H applied to C prime is greater than or equal to H applied to C when C prime is included in C, okay? All right. So, for example, Hartigan's tree has a canonical, if you want, height function given by this one here. You take effectively the level set where wait a second, yeah, that contains that cluster C. Okay. The upper level set, sorry. Is the level of the upper level set that contains C. There we go, I think. All right. So, right? So if we're given an endogram, so therefore a cluster tree equipped with a height function, then the merge height of 2 points is simply I think is the last. So if you go from lowest value of h to highest value of h, I think is the last value of the last cluster that contains both points, effectively. It's the height of the last cluster that contains both points. That makes sense. Okay. It's hard to parse this, but I don't want to go into too much detail on technicalities. It doesn't make sense in the context of the entire talk. But okay. So for the special case of the Hartigan cluster tree, again equipped with its height function as defined in the previous slide, is this one right here. So it's the supreme. So we have x and y. Okay. So sorry, x and y are here outside the supremum. The supremum is over C. Okay. X and y are given. So you could have C containing x and y, okay? But the supremum is over C, and what does C satisfy? It has to be connected and contains both x and y, okay? And then it's the height of C, which in the previous slide we saw was the infimum, right, of the value of f over C, okay? It is a bit hard to parse, so, I mean, but it does make sense. If you sit with it a little bit, it does make sense. I can promise that. But it can be, if you've seen this for the first time, it's probably difficult to digest. But anyway, it's called the merge distortion metric. It was proposed by people actually all three of them are colleagues of mine now for some reason. Justine Eldridge and then Misha Belkin and Yusu Wang. Okay, so what they do is for two dendrograms, they effectively compare their merge heights, if you want. Point-wise, but here a point is a pair xy. Okay. All right. So anyway, it has some properties that they elaborate on that paper where they introduced it. Anyway, it's I think it's a fine one to look at for comparing cluster trees. And what we're able to show is that. So given a continuous function, so again, what we want to do is extend everything to continuous functions, meaning that this finest somehow cluster tree, which we didn't define for continuous functions, we won't define for continuous functions, but if we approximate that continuous function with piecewise constant functions for which we did define those axiomatic trees, those trees converge to the Hartigan tree for that continuous function. Okay? So given a continuous function f with connected support, again, if the support is not connected, then it's not a big deal. It's just effectively treated separately, I guess. The connected components, you treat them separately. So we say that C is an axiom or axiomatic cluster tree for f if there is a sequence of functions in that effectively piecewise constant function, let's call them, that are a bit regularized, that uniformly approximates f and such that in merge metric, those axiom cluster trees for Fn equipped with their height function, the same one as Hartigan's, converges to that cluster tree C, also equipped with that same height function, the Hartigan height function. And what we're able to show is that if F is continuous function that admits at least one axiom cluster tree, in the sense that I just defined now, then its Hartigan cluster tree is an axiom tree, and not just that, but any other axiom tree is within distance 0 in merge distortion metric of Hartigans. Okay? So it's one thing that remains is when is it that the continuous function admits an axiom cluster tree? So effectively, that's the case for if the metric space is a Euclidean space. We come up with a condition that we're not really able to connect with anything in the literature we could find. But we're able to show that in Euclidean spaces with the usual metric, any continuous function admits a axiom cluster tree in the definition I just gave here. Okay? So therefore, this theorem applies. We don't know if it applies beyond that. We have strong suspicions that it applies if the space is, for example, a Riemannian manifold or something like that. As things tend to be the case, it tends to be the case, right? But of course, going from Euclidean to Riemannian carefully, we just don't think it's necessarily worth it given the amount of effort that would require. But we have strong suspicions that it applies beyond Euclidean spaces. Okay, and that's it. Thank you very much. Yeah, there's a question over there.
If you need a wireless mic, I have one right here.
Thank you for your great talk. I was wondering whether there is a result on reaching the global maximum of the density using mean shift or any other method that you studied.
So only if you're in the basin of attraction of that global maximum.
I mean,
right?
So we do have results on that, or?
So no, it's just by definition of basin of attraction. So if you start somewhere that's not in, it's in basin of attraction of a different local maximum, that's where you end up by definition of a basin of attraction. So, but we have another paper. In fact, we have another paper on finding the maximum, for which there's actually a very large literature as well. But it's not very connected to this. So it's because modes play such an essential role in modal clustering. The estimation of modes is also sort of like there. It turns out we have a little paper on that as well, if you're interested. I mean, I don't think it's groundbreaking or anything like that, but we do cite some of the literature, so you can have a look if you want. Yeah, and that's about finding the global maximum. Yeah.
Thanks for the interesting talk. Can you remind us, as I recall, when Pollard proved that Hartigan's k-means was consistent, he did so by...
Oh, David Pollard's consistent for k-means?
Yeah.
Yeah.
When Pollard proved that, right, so he sets up a population version of k-means,
yeah.
which it doesn't involve any densities, it just involves an optimization of some objective function that's applied.
That's
right. Now I noticed that formulation of clustering as just the solution to an objective function optimization is not part of your...
No, exactly.
Is there a reason you avoid that?
No, so it's... I mentioned it right here. It's this one right here, right? So it's a different way of understanding clustering. Also, techniques are quite different. It uses at least some basic notions of empirical processes, which play no role here, more or less, in what we do. At least, actually, they do play some role indirectly, because we do use some known results on kernel density estimation, and those rely on empirical process theory, but not in the same, not perhaps in the same direct way, perhaps. I don't know. So it's not like we avoid it or anything like that, it's just a different way of understanding clustering. Now, if you ask me, I can add a bit more to that, but that's a bit more subjective now. So, for me, k-means is not really doing clustering, it's doing quantization. And because it can, k-means, it's not even me, I mean, it's from reading Hartigan. He looks at things like complete linkage, hierarchical clustering with complete linkage, which some people tend to prefer to single linkage. And he criticizes it a lot, and he has some conjectures there saying that it more or less ignores the density. I don't think people have proved that, but they are. If you do numerics, so something that ignores the density, so it ends up quantizing the support, but not taking into account the density that much, if that makes sense. And it's, I think, problematic because of now, Sure, if we adopt this definition of clustering, either one of them, we now sort of argue, at least argue, that it's more or less the same definition, either Hartigens based on level sets, or Fukunaga and Hostetler's based on gradient ascent length, or flow. That's fine. I think it's a attractive definition of clustering. But the issue is that you cannot do it in dimension 5 or above, right? Because you have to estimate the density. And in principle, that's done under some smoothness assumptions only. So yeah, you run into trouble very quickly. And there's a Curson dimensionality that hits you really hard. Unless your density is super on the usual thing that to avoid that if you have some sort of structure, like the density, for example, naive Bayes structure, like is a product of its marginals, or the other one is that it's supported on some lower dimensional surface, something like that saves you. But so it's kind of a similar story that that's effectively the same for all kernel methods, pretty much, right? And local methods. So yeah, and then we can still do k-means, right? But k-means is bizarre in higher dimensions. I have another paper on that actually, and yeah, it's just like the geometry in high dimensions is just bizarre. Like the space is mostly empty of points, and it's bizarre to even look at distances. But anyway, people do that all the time, obviously. But it's pretty clear. K-means is a quantization. It does quantization and not so much clustering. Yeah, because it ignores. But anyway, we didn't really avoid it. We just focused our attention to this other area. But it's true. Like I could have mentioned David Pollar's, of course, seminal paper on proving that at least if you were able to solve the objective for k-means exactly, which is not obvious, then you're consistent in the large sample limit. Yeah.
Okay. Okay. Any more questions? So yeah, I have a brief, small comment. So, right now people in high dimension clustering is really a hot topic. Like this very high dimension and just all kinds of feature sparsity, so on and so forth. Is there do you think there's some connection between your work and high dimension clustering?
The sparsity, yeah?
Yes, sparsity.
Well, that's when you could assume some structure on the density.
Okay, okay.
So something like, a sparse structure on density, so something like, so there are multiple ways of doing it, but one way would be, so an extension of naive Bayes, so like you have, you have higher and higher level densities, but you just limit that in some way that makes it sparse in a sense. That's one way. Another way would be to say that actually, sorry, I was going to say something else that doesn't quite apply to density, sorry, but I was saying like in a ridge regression, but you can't really have that for densities. So I guess if they are supported on some compact set, you can have that. So possibly like it's only dependent on a few variables.
Okay.
Right, in that case you can have it if it's then supporting on the compact set.
Okay.
And yeah, so then in your estimation of the density, you can use that sparse structure, but I don't see it. So beyond that, I don't see it. Yeah. Okay. So and I should say, so Jose Chacon, who is one of the people working in this area, for example, in mix of the two, he has he assumes some structure of the density. I think he assumes that it's a mixture of Gaussians, in fact, but then does the clustering not based on the components of the mixture, but based on the gradient ascent flow.
Okay. Okay.
So so if you can assume some structure that involves sparsity, then you could be okay. Yeah, like the log density is sparse in some bases, for example, as well, that sort of thing. Yeah.
Okay. Okay. Cool. Okay. Any more questions? Okay. If there's no more questions, let's thank Ery again.
Yeah.
Okay.
No, thanks again. It's an honor. Thank you.